Next up, we have a Spanish telecommunication and systems engineer with a PhD in neuroscience. So now for something completely different. Last year, she moved from Barcelona to Oslo to join the Lifespan Changes in Brain and Cognition group as a postdoctoral research fellow. She enjoys being a part of an interdisciplinary research group, using advanced imaging methods to understand the healthy human brain, as well as the alterations occurring in aging and in neurodegenerative disorders. And tonight, she will talk about functional changes in the aging brain and show us some examples of how the old brain might cope with damage and keep working almost perfectly. Please give her a warm welcome on stage. Here's Roser Sala.
Hi, good evening. Thanks for the nice presentation. As she said, I'm going to talk a bit about the aging brain and especially how does it function with age. I will show you a lot of neuroimaging stuff. First of all, we all know that our brain would suffer from atrophy when we get old. So if we are 27 years, we would have a brain that looked like this. But if you get to 87 years, we know that we will lose a lot of gray matter and even white matter. And that especially these losses of neurons would be in the frontal cortex. And we also know that aging is related to Alzheimer's disease. And many people are interested on studying Alzheimer's disease and getting biomarkers to discover it, and also getting to some drugs to treatment. But I'm not going to talk about this today. This is a bit sad. I'm going to talk about what's happened with these people that perform well, even if they don't have as much gray matter as a 27-year-old. So which are the mechanisms that would help to this? So for this, we have neuroimaging. What's neuroimaging? Neuroimaging would be like putting a subject in a huge magnet and getting brain images as the ones that you get that you can see in the right. These images can be images of the gray matter or white matter, as we can see, like structural images, where we can see in the structural images, we can get the gray matter structures. We can delineate like the hippocampus or the cortical thickness, or we can get to white matter structures that could delineate like the fibers that connect the different brain regions. But apart from this structural imaging, we have functional imaging. And this functional imaging would tell us which neurons are active in the brain. So we could get to brain images showing which areas are active in a task. I will try to explain it with a brain network. So what's a brain network? Brain network is something that would look like this. And this is showing you the different connections that we can get in the brain. These connections can be functional connections or structural connections that would communicate different areas. But why this network? This is so nice. But what can it be important for us? Because it said that pathology, it's normally related to breakdown of some of these connections. So the network of a diseased patient wouldn't be the same as the network as a healthy patient. And why it can be important for us in terms of structure versus function. I'm not going to talk about brain structure today because we all know, as I have said before, that we lose a lot of structure when we get old, and this would deserve like another topic. But I'm going to talk about how can we strengthen brain function. So for example, let's take one task, one cognitive task. And we ask our subjects to perform this task while we record which brain areas would be active and inactive. And then we get to these brain networks. So if we perform this to a group of subjects, like young and old subjects, we can get to these kind of maps showing us the areas of activity. So what would happen is that in some of these regions, the old subjects that are able to perform the task, these super elders that I told you, would have more activity in some of these areas. For example, in this area, in the frontal cortex, I don't know if you can get to figure it out, we have some hyperactivations of these areas, and this would be what helped all subjects to perform well. But this is what happened during task. But what if we ask ourselves to rest, to just do nothing, like lying in your sofa? And we also record what's happening in your brain while you are not doing anything. And it happens that there is also a network interaction during this time. And we can get to the task shifting situation, where you have the task networks that would be active during task, but when you go to rest, you activate another kind of regions that are these default mode network regions. And why can this be important also in aging? Because we know that this resting state is not the same when you get old. So we don't rest the same. This could have many implications, but in neuroimaging, we see that these regions that are supposed to be connected get disconnected in aging. So we are resting and we go back to task. So what happens is that this default mode that would be off when you start doing the task keeps on in these old subjects that would be performing well. That means that it's part of these extra regions that will push your functional network. And all of this, I just tried to put an example of two networks, but all of this can be constructed and perform like all the brain. So if we pair all the networks, we get maps like this. And further on, we can just draw this in a brain-like figure and get something like this, again, to our brain network. And what could we get from this is that the long connections get lower with aging. So it's going to be more complicated to get from the frontal cortex to the posterior part of the brain if you get old. That's why we would say that old people, even if they perform well, they are slower because they need to travel longer paths between the different areas of the brain, even though they are still performing well, so they are still within this super elders group. So I think that was all for me.